Hi, everyone. My name's Andrew. I'm a reliability engineer at 2 Sigma Investments. A big part of my responsibilities at 2 Sigma include partnering with data engineering teams to design, build, and operate batch data pipelines. Today, I'm hoping that I'll be able to share some of the lessons I've learned at 2 Sigma building resilient and more operator-friendly data pipelines. I also hope to give you a look at reliability and resiliency from the perspectives of a data engineer. Note, none of this is investment advice. What is 2 Sigma? 2 Sigma is a systematic investment manager that structures and analyzes the world's data, looking for new and better investment opportunities. Basically, this means that data fuels our business, and data pipelines are the means by which we transform and transport that data. That also explains our need for resiliency and reliability in our data pipelines. So what are we going to talk about today? Well, I'm going to have a little brief intro to pipelines, a pipelines crash course for those of you that are unfamiliar with data pipelines, or maybe a refresher for some of the rest of you. And then we'll actually go into several areas about designing resilient data pipelines. So first off, what is a data pipeline? Well, we have a textbook definition, a collection of data processors with directional dependencies and no cycles. Maybe it's better to just ask, what does a data pipeline do? And we have another textbook definition, but in plainer English, data pipelines automate the steps that would historically have been done by engineers and analysts to make data, raw data, both usable and accessible. So I'm going to show an example of one of the most common types of data pipelines to kind of hammer this through, which is just a simple batch ETL pipeline, or an extract, transform, load pipeline. This is a simple linear pipeline composed of 3 simple stages. In those stages, you might extract data, transform it in some way, and then load it into some destination. The important thing to see here is that data flows through the pipeline. It moves from origins to a location that it's accessible by its data consumers. And through that pipeline, it goes through multiple data processors which transform or otherwise modify the data or move that data. So that was just a theoretical example. What are some real data pipelines that we actually use day to day? Here are several examples of data pipelines that my team actually owns and operates, alongside some of the characteristics of those pipelines. So we have trading day analysis. At the end of trading each day, we want to produce reports and summary statistics that we can provide to our portfolio managers. And it's important that we get those reports to them prior to the next day's trading so they can make business decisions based on them. We have a research environment build process where we take the new data produced throughout the week, munge it to put it into a usable form or into a location that's accessible to our consumers. And we also even have tests, so trading platform integration tests. Our trading platform itself is a live data pipeline. So the integration tests for that platform themselves become pipelines. Here, it's not even on a frequency. This is on demand as our engineers are developing new features or as we need to test changes that are going to go into the production data pipeline. So what are some of the common concerns that operators of data pipelines have? Well, we're always concerned about how to understand and detect failures in our pipelines. We want to know how to recover from those failures. We want to know how to make updates to our pipeline while minimizing the risk associated with those updates. We know pipelines aren't static things. Data changes, as well as means of transforming that data. There are going to be changes to the pipelines we deploy to production. And finally, how do I know that the data I generate is good? The end goal of pipelines are to produce data usable by our data consumers. It doesn't matter if our pipeline succeeds if the data is unusable by our users. So keep these concerns in mind, because we're going to hopefully revisit them at the end of the talk to see if we have any ways of mitigating or addressing these concerns. So let's dive into observability. This should be familiar to a lot of you. Now, we're going to be talking about observability from the pipeline perspective. So here, we want to understand the state of our pipelines from whatever external outputs it makes available to us. How do we achieve better observability? Well, we do so through logging, metrics collection, and status monitoring. The pillars here aren't that much different from monitoring any other kind of service. The details are a little bit different, though. So with logging, what does this provide us? Everyone should know this. It's a record of events. It helps us to understand when and why things occurred. In the context of data pipelines, that can help us answer questions such as, why did this pipeline task fail? When was this pipeline scheduled? Etc. In addition to your regular logging best practices, here are a few things that you might want to keep in mind if you're adding logging to a data pipeline. You need to ensure that all of the data processors in your pipeline produce logs. Many times you may not actually be the technical owner of the processor that you're using, or maybe you're bypassing through a service. You need to ensure that there are logs for that service or that processor, because otherwise you're going to be sorry down the road when you're trying to answer a question of how some data was generated. You want to make sure that whatever you're using to execute or schedule this pipeline and its tasks produces logs. And for batch data pipelines, which have a life cycle, you want to make sure that your logs persist for at least some amount of time after that pipeline execution. They shouldn't just disappear out from under you. It's important to have access to those logs to answer questions after the fact. And I'm going to have an example of why that's important in a couple slides. Moving on to metrics collection. Here, there's a couple important things to think about. There's what types of metrics should I be collecting? If you took a look at any of those example SLOs on the previous slides, you might realize that latency is very important. But there are other things. These are just a few examples. We internally might care about what percentage of that latency is due to queuing if we're using a shared resource, like resource cluster. And we might also care about the resource footprint of our pipelines. And the other thing to care about is at what level we should be collecting those metrics. And I don't mean like debug, log, info, warn. I mean at the task level and at the pipeline level. And why is this important? So let's take a look at some of these metrics in practice. So if I want to look at pipeline latency, here I have on the vertical axis latency in hours, and on the horizontal axis I have several days of time. This was just a few weeks ago. And I'm going to be looking at the latency of a single daily ETL pipeline, for instance. Here I'm plotting the first couple instances of this pipeline. It's nearly a horizontal line. These first 2 days, this pipeline pretty much took the same amount of time to run. And we might expect that if it's been a stable pipeline. We haven't made a lot of changes to it. We haven't seen a lot of changes in the input data to it. Now, what happens when I plot the next 2 lines? Well, now we see this big jump in latency in this pipeline. It's now taking several hours longer. I haven't charted any kind of SLO threshold alert here or not, but it could be that this jump in latency actually pushes us over our threshold. Maybe we're breaching our SLA at this point in time. So this chart, the metrics we've collected on our pipeline are very important for ensuring that we're meeting our SLA, that we have some visibility into the amount of time our pipeline takes, and we can detect when there's some kind of degradation in our pipeline's performance, but it doesn't really tell us why it's performing worse. Now, when we combine this with metrics that we've collected at other levels, like task latency, we can start to put together a story. So here I'm going to show a chart that also has latency on the y-axis and time on the horizontal axis, but it's going to show us the actual tasks within this pipeline and their latency. So when we look at this chart, what we can see is that there's essentially two groupings of tasks. There's a grouping of tasks that appear to take the same amount of time over this entire time period. And then there's a second grouping of tasks which have a corresponding jump, a jump that appears to be correlated with the increase in our pipeline latency. Now, to put the story to a close, we can take a look at the logs that we've kept for these tasks and realize that all of these tasks use the same shared resource, which had a degradation in performance over this period of time. So that's why we really need all these levels of visibility into our data pipeline, so that we can truly understand what's causing them to perform and behave the way that we're seeing. The last thing to keep in mind is status monitoring. We want to monitor our statuses at both the task and pipeline level for similar reasons. We want to keep track of status over time and across pipeline instances. We need to be able to distinguish the status of 2 or more concurrently running pipeline instances. And we should be making use of states. So this isn't like a service where we only are concerned with up-down. I mean, we have similar things kind of running and failed, but we have a lot more rich information that we have access to if we only use states. There are a whole other plethora of other states that can tell us a lot more about our pipelines, as long as we make that available to us as observers and operators. So now I'm going to talk a little bit about the structure of our pipelines. Now, to keep this talk 30 minutes, I'm going to only talk about a couple of the most important properties of tasks and input data. I could probably have a 30-minute talk just on this section, but I'm going to keep it to the 2 most important concepts. The first thing is idempotent tasks. A task is idempotent if when given the same input, it always produces the same outputs, no matter how many times it's run or rerun. A simple example is updating a database column to the nearest integer. If we have data that looks like this, some float numbers, on the first run of this type of task, we round everything and we get data that looks like this. On the second run and all subsequent executions of this task, we continue to get the same result. Now, a simple example of something that isn't idempotent would be just naively appending rows to a CSV. If we have data that looks like this, on our first run, we add a single row of new information that we've gotten in today. That looks all fine, but on our second and subsequent runs, we're simply going to be appending duplicated data. Now, I'm going to get into why idempotent tasks are important shortly, but I want to introduce one other concept first, and that's immutable inputs. So what makes data immutable? Well, data that can't change after it's been created is immutable. So data that cannot be modified after it's been created. Okay, why do we need immutable inputs then? So this would be input data that can't change. How does that help us? Well, we just got done talking about idempotent tasks. Tasks where, when they're given the same inputs, always produce the same outputs. Combine these two, and you're ensuring reproducibility in our pipelines. Now, what are some ways to ensure immutability in our inputs? There are some easy ways. We can simply version our data. We can use immutable data stores. A lot of the times, these just simply cost us more money in disk than in complexity. What are the concrete benefits of idempotency and immutability in our pipelines? Well, the deterministic nature of our idempotent tasks makes testing them a lot easier, and even chaining them and testing pipelines as a whole. But what I think is even more important is that it allows tasks to be retried without unintended effects. This reduces instances of operator error. We no longer have operators being concerned with whether they need to clean up some state from a partially successful task or a failed task. They don't know how long it executed. Do they need to remove some state or roll back a database before they rerun that task? No, they can simply feel empowered to retry the task first thing and then maybe investigate something. It's going to reduce our instances of human error considerably. And notice how I mentioned we can just tell them to retry it first and then ask questions later. If we're doing that with our human operators, maybe we can take those operators out of the question entirely. This actually facilitates automatic retries. So instead of having a human operator having to manage our data pipelines, we can simply let the computers do it for us. No more 2 a.m. phone calls. And it also facilitates checkpointing, which allows for a pipeline retry mode where execution of previously successful tasks are skipped entirely because we are confident that they would be simply producing the same data. So now I want to talk a little bit about pipelines as code. So what does pipelines as code mean? Some of you that have used Jenkins before might be familiar with this term already, but it simply means defining or representing our pipelines in configuration or code. And how can we accomplish that? Well, our data pipelines can actually be expressed as directed acyclic graphs, or DAGs. If you remember that textbook definition from earlier on, I know you do, our data pipelines are collections of data processors with directional dependencies and no cycles. If we treat our data processors as the nodes in our graph, and the directional dependencies as our directional edges, then we have a directed graph. And the fact that we have no cycles means that we have a DAG, a directed acyclic graph. Why is this important? Well, we already know how to encode DAGs as in declarative configuration. And we also know how to generate DAGs using any general purpose programming language. Now, what does this actually look like in practice? Here's an example of a declarative pipeline that I've written up. I've written it up in YAML simply because it fit on my slide easier, but it doesn't have to be YAML by any stretch of the imagination. And here I've taken our extract task from our sample ETL pipeline, and you can see what a task might look like in declarative configuration. We have some general information, a name, some unique identifier, a description, or some other embedded documentation. We might have some execution information that we pass on to our scheduler, such as what host group we want this to run in, what user or role account should this be running as, the actual command we're running. We might have constraints on this task, like how long we're willing to let it run for. We can enable automatic retries for it and tell it what conditions should trigger that automatic retry. The extract task happens to be the first task in our pipeline, so it has no prerequisites in this list. But you can imagine the transform or load tests having an entry in this list. The transform task, for instance, would have the entry 1 because it depends on the extract task, which has the ID of 1. We can have alerting information at the task level. Here it just emails me if it takes longer than 30 minutes and when it should be triggering an alert. And we might even have some resource information for our scheduler. Now, that's just a single declarative task. How do we put this into a pipeline? The pipeline might look something like this. And the first thing I want to draw your attention to is the tasks list on the right side. Here we have our actual tasks, the extract, transform, and load steps. The ellipses here are just to indicate that's where you would put the definition that I showed previously. This also has general metadata associated with it. It has a name, its own owner, a description. But something that it has that the task does not is some scheduling information. For instance, if this is a batch pipeline. This one's just using a simple cron string to tell us that it's going to be running at 8 a.m. each day, UTC time, and that it can handle running concurrently with other instances of itself. So some pipelines depend on the output of previous instances of the pipeline, and those cannot handle being run concurrently. But this one, for instance, doesn't care about that. So what are the actual benefits of encoding our pipelines in declarative configuration or generating them using a general purpose programming language? Well, it allows us to store our pipelines in source control. This gives us peer review through code review of all of our pipeline updates. It gives us a history of changes and ideally commit messages linked to those changes, explaining the purpose of those changes. And it actually makes it possible for us to keep our pipeline alongside the code it executes. So what do I mean here? It means that we can possibly actually store the definition of our pipeline in the same repositories as the data processors themselves, so that when there's a change to the data processor that requires a change in our pipeline, or vice versa, we can actually review them in the same code review, and actually have possibly the same commit. It's going to make it a lot easier for operators to understand why changes were made in our pipelines. This also gives us access to static analysis of our pipelines. We can actually enforce standards or other rules on our pipelines. Things like every pipeline must have an owner. Every pipeline has to have description or links to other documentation. It's going to increase the overall quality of our pipelines. It's also going to help standardize what a pipeline looks across our company. This helps support automation of pipeline deployments and rolling back bad pipeline updates. And this one's a little bit stranger, but it can help towards regenerating historical pipeline outputs. So if we have the exact pipeline that was run at a historical point in time, we also keep our immutable inputs for all of time, and we have idempotent tasks, it's easier, at least feasible, to be able to do this. There's other things outside of our control that may make this impossible, but otherwise it would have been impossible beforehand. So the last thing I want to talk about is data validation. So if you remember earlier on, I said that data pipelines automate the process of transforming raw data into usable data. So then what is usable data? So we have another boring definition for that. It's data that can be used for its intended business purpose, but that's not very helpful. It might help more to understand what makes data unusable. And for that, I have this little table example. I have this little price and currency code table. It looks quite usable to me, but my users tell me there's a lot of problems here. In this first entry, they tell me, well, while it's technically correct, I'm expecting a number, so it doesn't adhere to the format that I depend on. In the next entry, they say the price can't be negative. This is just wrong or impossible. And in the last one, they say, we're missing the currency code. This data is incomplete and meaningless. We don't know whether this is in dollars, euros, or pesos. So something that can happen frequently is actually that a previous consumer might have been okay or assumed a currency code in this situation, but the new consumer requires it. So it's very easy for these types of failures or unusability to occur in our data. So how do we ensure that the data we're generating is usable for our data consumers? And that's where data validation comes into play. What is data validation? Well, this is the process by which we ensure our data is usable through the use of data validators. Data validators are special data processors which validate, verify, and test their input data. There's a lot of different types of data validators. We have data type validators. These ones are ones that confirm that the data adheres to the expected type. When we expect an integer, we get an integer. When we expect a float, we get a float. We can have constraint validation. This is, for instance, that the price is greater than 0. This can be also regular expression checks, that a phone number adheres to a certain regular expression. And we can have more complex quantitative validations that may require more sophisticated domain expertise to actually construct. An example of one, if we looked at these two different price tables, this is going to be showing the price of, let's say, a stock over time, over a short period of time. And what we actually see here is that the table on the left might be something we expect to see, and the table on the right seems to have a problem. We see a huge fluctuation in price in a very small time delta, which is something we wouldn't expect to occur usually. So we can actually write more complex quantitative validations, such as like adding some autocorrelation checks to this data, to essentially give a pass on the data on the left while failing the data on the right and preventing it from ending up in the hands of our consumers. So what are the pros and cons of data validation? The pros should be fairly apparent. We get to provide some level of guarantees on the usability of our data. We can detect soft failures in our data pipeline. These are situations where tasks are succeeding, but the data we're generating is invalid. And by the end of the pipeline, our consumers will be ending up with data they can't use. And now that we can detect soft failures, we can turn them into hard failures and actually prevent the execution of downstream tasks using invalid data. It sounds great. So what are the cons? Well, they can increase our pipeline latency. If we put these validators into the critical path of our pipeline, some of them can take a really long time. Some of the complex quantitative validators can take a very long time to to run. And we can actually introduce flaky validators. This can happen in a number of different ways. The validator itself, the assumptions made when we created that validator are not actually valid. We were wrong. The data that comes in actually changes over time, and our previous assumptions are no longer correct. Or just something within the validator itself, poor coding. So how do we add validators to our data pipelines while mitigating these risks? Because the pros seem so good. One method that we use is called the quarantine method. Now here, new validators are always added as leaf nodes to a data pipeline. This ensures that the validator is not on the critical path. It's not going to affect our pipeline's latency or reliability, but that we can still generate reports from it or trigger alerts or inform us about the validity of our data. And then after watching it for several execution cycles for a batch data pipeline or just watching it in live for a while, we can make the determination of, we have several different options at that point in time. We can choose to continue to run the validator as a leaf node outside of the critical path. We can actually move it into the critical path to now turn that soft failure into a hard failure. Or if we find that it's flaky or that our underlying assumptions were incorrect as soon as we exposed it to real live data, we can simply remove it. So now let's revisit those common concerns I mentioned earlier. Do we now have some tools or other knowledge that we can use to mitigate some of these concerns? If I'm interested in detecting and understanding the failures in my pipelines, can't I improve my observability of my data pipelines? If I'm worried about how to recover quickly from pipeline failures, if I've ensured that my tasks and my tasks are idempotent and I'm using immutable inputs, that goes a long way towards improving this situation. If I want to minimize the risk associated with changes to my pipelines, then I should probably be using pipelines as code so that I get a free history of changes, I get code review and static analysis. And how do I know the data I generate is good? Well, that's because I validated it using data validation. So thank you all. We actually have several minutes, so you don't have to meet me outside. If you'd like to ask a question, feel free.
If you have any questions, please come up to the front, to the mic.
And otherwise, I'll be at the 2 Sigma booth, so you can always just stop by.
So how does this apply to situations where you require very low latency from end to end? For the pipeline task, like you have to be below 100 milliseconds.
Oh, sure. Oh, yeah. This is a fun
question. Declarative programming for that purpose.
Sorry, so what was that last part again?
How do you apply this kind of a declarative?
Yeah, so the question was, okay, how does this apply for low latency pipelines, times where the end-to-end latency of this pipeline is very, very short. So there, I apologize that I kind of didn't have the time to go into more of the stuff that's important for live data pipelines. There are different things that matter for the structure in that situation. So in the situation where we have low latency pipelines, we may be more concerned with the actual structure of the tasks that we're executing themselves. We may want to be collapsing tasks, so minimizing the number of syncs that we hit, or reimagining the ordering of the operations that occur. So a lot of times people talk about ETL pipelines. There's also ELT pipelines where we do the extractions and load into our actual data destination and do the transformations at that level. Those types of things are what I consider more important for low latency pipelines. You can still define your pipeline in declarative configuration, because at some point when you're updating the pipeline, you have a deployment process that knows how to translate that configuration into deploying the different components of your pipeline. And it's still going to help you to understand why changes to your pipeline were made and when. Any other questions?
All right. Thank you, Andrew.